Hi everyone, so this is polarity and VSEPR shapes. So just a quick reminder about the three different types of bonding. So we have ionic bonding, which is an exchange of electrons between two atoms. Typically a metal loses electrons to a nonmetal. We have covalent bonding, which is equal or approximately equal sharing of electrons between two atoms, typically two nonmetals. And then we have polar covalent bonding, which is unequal sharing of electrons between two atoms, again, typically your two nonmetals. So how can we check for polarity? So we're looking for the difference in electronegativity between the two atoms involved in the bond. We're looking at the electronegativity value, which is usually a small number. It could be anywhere on the periodic table, to be honest, in each of the boxes. In the textbook is underneath the atomic number, but depending on the periodic table, it could be in lots of different places. Noble gases often don't have one, they have a strike. So if we do have a noble gas, which we sometimes do, we're going to use the value of 0 to work that out. So in terms of our difference in electronegativity, if that difference falls between 0 and 0.5, we're going to consider that covalent. If it's 0.5 and 1.7, between 0.5 and 1.7, we'll consider that to be polar covalent. And specifically, if it's 0.5, we'll call that polar covalent. And then with ionic, it's going to be greater than 1.7. And if it falls directly on 1.7, again, we'll consider that to be ionic. So polar covalent molecules are really the tricky ones here. If electrons are not being shared evenly between two atoms, we have one atom pulling harder on that electron pair, and it's going to become slightly negative. And then we have the other atom that's kind of holding on for dear life, and it's going to become slightly positive. And this is called a dipole, and it can be drawn in a couple of different ways. So the grade 11 model is just sort of showing this sort of slight negative and slight positive, and they're kind of like curly S's that you do. And then the grade 12 method is to draw a vector. So a vector is an arrow showing a size and a direction. And this is more helpful when we're working through shapes and why certain dipoles cancel and why they don't. So in this case, our oxygen has a value of 3.5. and our hydrogen has a dipole of 2.1, or an electronegativity of 2.1. So the larger value is the one that is hogging the electrons, so it will become slightly negative because it's stronger pull on electrons, and because electrons are negative, that's why it's slightly more negative than the hydrogen. So let's try these ones. We'll call them A, B, and C. And of course you can pause and try them on your own and then play the video back to see if you're correct. So we're going to check the electronegativity values first. So our boron is a 2.0. Our fluorine, our fluoride, is a 4.0. The difference in electronegativity then is 2.0. And that means that we have an ionic compound when we check the table. Let's try the next one. We have sulfur, which is 2.5. We have chlorine, which is 3.0. Our difference in electronegativity then is 0.5, which is the low end of our polar covalent scale. Since it's polar covalent, we're going to do the additional step to draw our dipole, and the dipole points to where the electrons are going to be. So the one that has the higher number is pulling electrons higher or more strongly, and the tail gets the positive sign since it will be slightly positive. Our last example, phosphorus is 2.1. All right, so our next one is phosphorus. It's 2.1. And our oxygen is 3.5. Oops. So we have a difference in electronegativity of 1.4. So again, another polar covalent. And again, because oxygen has the larger electronegativity, it's pulling harder on the electron pair. So it's going to be slightly negative. We point towards where the electrons are going, and the phosphorus will be slightly negative or positive. So now let's tie the two things together. So we looked at shape already, we've looked at polarity together, and now let's look at the two of them combined. So step one, we are always going to do. Step one means we check the electronegativity difference, and if it's ionic or covalent, the question of polarity is already answered. You do not have to go to step two. If it's polar covalent, so let's say in step one it's polar covalent, now we're going to go down here and we have to check shape. So we're going to have a look at how shape and polarity are related to one another. Some polarity can cancel. It is a force. It's a push or a pull. And so you can cancel forces by having equal and opposite forces. So some shapes offer that sort of advantage. Look at our general rule. The general rule applies to when all surrounding atoms are identical. This is the more common case, but certainly not the only case. So this rule, these set of rules we're going to look at, only apply to when all surrounding atoms are identical. Then we'll have a look at what happens if they're not identical. So the general rule is this. Nonpolar means that dipoles cancel out because of shape. The shapes that do this are all my parent shapes plus square planar. They all have something in common. They all have this symmetry about them in which they have equal amount of push and pull if the surrounding atoms are equal, and so they end up canceling their dipole effect. There is an unbalanced set of forces when it comes to kid shapes, except for square planar. And so when we see examples here, we're going to notice that the dipoles do not cancel because of shape. And if they don't cancel, the dipoles are still there, and that means that we have a polar molecule. So let's have a look at this in more detail. So let's consider the following parent shapes. The easiest two shapes where almost all the other shapes come from are going to be my linear and my trigonal planar. Let's start with my linear. I'm going to use a fictitious compound XY2. And I'm going to draw some dipoles. And these dipoles could be going out or in, and it wouldn't make a difference. The analogy here to understand why these dipoles have a canceling effect is, imagine I'm X, I'm standing in the middle of two people, and they're each pulling equally in opposite directions on my arms. I wouldn't move, and that's because the pull to the right cancels out the pull to the left. The same thing is happening here. Dipoles are just a pull of electrons. So the pull tugging the X to the right is canceled out by the tug pulling to the left. So that's the analogy. Mathematically, and using vectors, if you've done some physics you would have seen this, I can add the vectors one after the other. So vector addition has a set of rules. It means when you draw the first vector, so I've just replicated this first vector here, I've put it over here. Wherever I stop drawing the first vector, I start drawing the second vector. So now I'm going to take the second vector and I'm going to draw it directly after the first vector. Because it goes back to the beginning, it means it's proving that there is no, or let's actually just say it this way, it's easier, dipoles are canceling. So that's what we're showing here, is that the pull from opposite sides ends up going right back to the beginning again. So there's no overall pull. They cancel each other out completely. So therefore, what we can conclude is that this molecule is a non-polar molecule overall. So that means it will behave like a non-polar molecule. So non-polar molecules, for instance, don't dissolve in polar solvents. And all the other characteristics that a non-polar molecule would have, this particular molecule would have those same characteristics. All right, let's have a look at trigonal planar. If we can understand these two, all of the rest of them pretty much fall in line. So then let's go back to our fictitious molecule of X's and Y's here. We'll put in our dipoles. Again, they could go in or out. I'm just going to make them go out for consistency here. Again, if we had a person in the middle, let's say it's me, and we have three people around the outside and they're all at the same equal angle to each other and they all pulled with the same strength, again, I would not move here because of that balance of forces. Again, because of that balance of forces, the fact that no force here is greater than the others and there's no overall effect on the central atom, that means that the dipoles are canceling. To prove this using physics, I'm going to do the same thing I did above. I'm going to take one dipole at a time. I'm going to add them together to see where we get. There's the first one. I'm going to go to this one down here next. I'm going to put in just sort of the same angle. I'm going to attempt to make the same angle. And then I'm going to put the third one in next. It's kind of going up like this. Oh, that one was going down. Never mind. Hold the phone. Hold the phone. Let's try it again. All right, there's the first one. There's the second one. There's the third one. That's better. So again, since dipoles cancel, we can conclude that this molecule would be non-polar overall. And again, it would have the characteristics of a non-polar molecule. So these two shapes make up almost all of the other shapes. Let's have a look and see how that works out. We're going to skip tetrahedral. Tetrahedral is going to hurt your brains unnecessarily. We can have a chat about that one-on-one if anyone is interested in that. That's a little bit more advanced physics. So if you've done some grade 11 physics, we can definitely have a chat and you'll probably be able to get your head around it. But let's stick to the other shapes because that's really all we need to know for a grade 12 level in this area. So let's consider, we're skipping tetrahedral, let's consider trigonal bipyramidal. Well, if we have a look, trigonal bipyramidal has a linear. And we know that if the surrounding atoms are equal, we have our first scenario there, an X with a Y on either side pulling equal and opposite. So we know that this will be nonpolar. And then we have a flat triangle in the middle. And again, so long as, whoops, can't talk and write, trigonal planar. So long as the surrounding atoms are equal, same thing as the second example where that triangular effect will cancel the dipoles. So that's why trigonal bipyramidal then would end up canceling its dipoles so long as all the atoms were, surrounding atoms were the same. Octahedral is just 3 linears. So again, since we know linears cancel, if I had 3 linears, same thing, they would all just cancel. Again, all of this is dependent upon the bonds being equal and opposite. Again, we'll look at exceptions to the rule shortly. Let's consider some of our kid shapes now so we can understand why kid shapes are polar, why they don't cancel. Let's consider the easiest kid shape. Let's go to a bent. And bent could be with 1 set of lone pairs or 2. I'm just going to keep it simple if I can actually make dots. There we go. Geez, that took a while. Let's just keep it simple with 1 lone pair, but 2 lone pairs would work the same way. So let's again consider that I have 2 dipoles in opposite directions. Well, they're opposite in direction, but they're both pulling down, and there's nothing opposing them. There's nothing going up. And so, for instance, if I were to add them together, I'm going to do the one on the right first, and then I'll do the one on the left. They don't go back to the beginning again. So they might have some partial cancellation since they're going right versus left, but they're also both going down, which is additive. So they do not cancel. So I can say that dipoles do not cancel. Therefore, this will be a polar molecule. Let's try another one. Let's consider a seesaw. Whoops, I didn't put my X in the middle. Let's do it now. There's a Y, there's a Y. Let's put my lone pair over here, and we'll have a pair of Y's there. So again, I have this linear section here. So we know that part can cancel out. But if I have, let's say I consider this section right here, even though I might draw dipoles here, those first 2 dipoles will cancel. But in that section that I just drew right here, if I have a look at it, it's just a bent. So it will not cancel for the same reasons why bent by itself will not cancel. Let's consider T-shape. So here's T-shape. Take one more bond off. And again, this linear section will cancel, but this section, there's going to be no cancellation here. There's nothing to cancel that one dipole. There's nothing opposing it, and therefore it will just be a dipole by itself. No cancellation means polar. So polar over all. And that's why kid shapes generally are going to end up being polar. Now there's one kid shape that defies the general rule, and that is square planar. So let's have a look at that one. Square planar. Let's throw some dipoles on here. Square planar is just two linears. So again, that's why square planar ends up hanging out with the parents in terms of polarity, because linears will cancel, and therefore overall this shape will end up canceling. Let's try some real examples from the beginning. So again, this should actually be NCl lower 3. We're going to go right from a Lewis structure, and we're going to do the entire content. So what we need to be able to do is we need to be able to do the Lewis structure, transitioned into a good copy with the correct VSEPR shape. We want to be able to name the shape and then determine overall polarity. Let's put it all together. So nitrogen is 5 plus 3 chlorines at 7 electrons apiece for a total of 26 electrons in total. Let's set it up. Nitrogen in the middle. We'll put our chlorines symmetrically around the outside. Our first electron pairs will go between center and surrounding. Then we will put in our octets for our surrounding atom. Stupid pen, come on. Ugh, come on, go, just one more dot. Just one more dot. Oh, jeez. All right, and then we count. So I have to make 2 more dots, sadly. I have 24 in the picture. There are 26 electrons that I'm supposed to have in the picture, and leftovers, as we know, go on the central atom. So at this point, I'm now going to transition into a good copy with the correct VSEPR shape. So I'm going to count all of the electrons on my central atom, and I'm going to start with my parent shape to work out what shape it should end up in the end. I've got 4 pairs. 4 pairs tetrahedral, 1 up, 3 down. Now I'm going to take a stick off and replace it with a lone pair so that I can figure out what to draw this like. The lone pair will push those 3 legs down still, so I get this little mustachio guy. So let's draw this in the correct form now. Nitrogen in the middle with its 2 lone pairs. Then my legs are all down. And then I've got my electrons. Oh my gosh, I'm going to pause so you don't have to watch this terribleness. It's painful. All right, so there's my Lewis structure. So I have 2 more pieces to include. I want to include the name. This is called a trigonal planar. So that's the next piece. The last piece I need to show is the overall polarity. So once again, there are 2 steps here. Step 1, I have to do regardless. I have to check the electronegativity difference. So let's do a little bit of side work here. So my nitrogen is a 3.0, and my chlorine is a 3.0. Therefore, my difference in electronegativity is a 0. Therefore, my overall polarity, ooh, that's not how you spell polarity. Polarity is covalent. Or we could say nonpolar if we wish. There's example number 1. Let's try another one. This one is SF4, so Fs is 6 plus 4 times 7. 34 electrons to put into our picture. Let's start with our central atom. We'll put the fluorine symmetrically around the outside. And we'll put our first set of electron pairs in. I'm going to do electrons without you. Give me a moment. I saved you from that painfulness. We have all of our electrons placed accordingly, and now we're going to check our electron count. So there are 32 in the picture. There should be 34. So we're going to put the extra ones on the central atom. I've just made them a different color so they stand out a little bit for us. And now we're going to transition into a good copy since we have at least an octet. And I'm going to just circle up my electrons to figure out how to draw this picture. So I've got 5 pairs of electrons. So 5 is trigonal bipyramidal. So there's where I start. Now I'm going to pull off 1 stick and replace it with a lone pair so that I can see the resulting shape that I need to create. So this shows me that I now have to create a seesaw shape. So I'm going to start going to town here. And I'm going to pause it to put in my electrons. There we go. And I'm going to name it. That's the second piece I want to see. Seesaw. And now I'm going to work out my dipole action. So I've got an S-F bond here. The S has an electronegativity of 2.5. Fluorine is a 4.0. So my difference in electronegativity is 1.5. Now I'm going to determine whether these dipoles would cancel or not. So because it's a kid shape, dipoles will not cancel. And if you have a look, the dipoles will cancel through the linear section, but not through the bent section, just as we did in a previous example. So since dipoles don't all cancel, some cancel, but not all of them. That's the key. You just have to have some dipoles still in the end. So since dipoles don't cancel, this molecule will be polar. So polar molecule. Let's try this last example. I've just rewritten it for us with the subscripts and superscripts, since this program doesn't do that. So we've got PO4 3 minus. Let's put an electron count together. So we've got 5 plus 6 times 4 plus another 3. Total of 32 electrons. Again, we'll start with phosphorus in the middle, our oxygens around the outside, electron placement time. So we have put the electrons in. There are 32 electrons in the picture. There's supposed to be 32 electrons. So now, and there's an octet. We always check that as well. So now I've just circled my electrons. I have four electron pairs. So that shape is a tetrahedral, and it's going to stay as a tetrahedral since I have no lone pairs. So let's draw it as such. So P, O, 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 O. Let's put in electrons. And we also don't want to forget this one is an ion, so we need that extra step 6, which is square brackets and a charge. And again, my next step is to state the shape. So this is a tetrahedral. And now it's time to work out polarity. So I'm going to go to my PO bonds, and a P is a 2.1, oopsies, and an O is a 3.5. So my difference in electronegativity is 1.4, which means it's polar covalent. So because my bonds are polar covalent, again, I have to check the shape. So the shape is a parent shape. And I didn't show you how a tetrahedral works out. You're just going to have to trust me. We can have a conversation about that one-on-one if you need to. But because it's a parent shape, dipoles will cancel. Since they're all equal, they're all going to be 1.4. They're all going to work together to cancel. Therefore, this will be a non-polar molecule. All right, let's have a look at some exceptions. So a shape which is normally non-polar can be made polar if the dipoles don't cancel. So what we're talking about here are parent shapes, because usually parent shapes will cancel their dipoles, but it's possible that they don't cancel. And that's going to happen if surrounding atoms are different. So again, think back to that example where I have X and Y, but instead of X with two Y's, let's say I have an X and a Z. And let's say that X and Y have a dipole going in this direction. And let's say that X and Z have a very big dipole going in this direction. Now, if I'm the person staying in the middle and person Z is pulling with way more force than person Y, I'm going to fall towards person Z. I'm going to feel the effects of that pull. So those dipoles are not canceling. So this molecule would be polar overall since the dipoles are not going to cancel. So anytime you don't have equal dipoles, this is the outward effect. And again, if I wanted to show this with physics, I could add them up, and you can see they're not going to completely cancel. Show an example of how that one would work. Again, I'm just going to rewrite it here for us. CH3Cl. Same approach as always, so I'm just going to start with my valence electrons. So 4 plus 3 times 1 plus 7, giving us 14. And again, I'm just going to put the carbon in the middle. Carbon would go in the middle as opposed to chlorine, because chlorine already has 7 electrons. It only needs to share once, whereas carbon has 4 electrons. It needs to share 4 times. So I'm going to have a chlorine and 3 hydrogens. It doesn't really matter where you place things at this point. And then our electrons. So I've put my bonding pairs in and my octet just for chlorine. Remember, hydrogen doesn't need an octet. And then from here I'm going to count. So I have 14 in the picture. I'm supposed to have 14. Carbon has an octet, so I'm going to go to the good copy. So again, I'm just going to look at my electron pairs on the surrounding, or the central atom. There are 4. 4 is tetrahedral. No lone pairs, so I'm just going to create a tetrahedral now. Here we go. And then, that wasn't too bad. And then I'm going to name the shape, so tetrahedral. And this time for the polarity, I have to check 2 types of polarity. So I have CH bonds, and I also have a CCl bond. So I've got 2 dipoles to check. So let's check the carbon hydrogen first. So carbon is a 2.5, hydrogen is a 2.1 for a difference in 0.4. So this one is non-polar, or we can say it's covalent. The carbon again is 2.5 and the chlorine is a 3.0. So the difference of 0.5, and this is a polar covalent bond. And if I draw it in here, it's going to go towards the chlorine here. You'll notice that even though this is a parent shape and typically dipoles would cancel, when you only have one of them, there's nothing to cancel it. So overall, you can see here, overall this will be a polar molecule, because unless all of the that's kind of ugly. Unless all the dipoles are working together, we can't cancel out. So that's how that works. One more. So BCl2 Br. Let's do our electrons. So we've got 3 plus 2 times 7 plus another 7. Let's see, what's that? 21, 24. All right, so we'll put boron in the center. We've got 2 chlorines and a bromine, so I'm going to put the 2 chlorines on either side and the bromine on the top. Let's put some dots in. So we count up our electrons and we have 24 electrons. Typically, remember, we would check for octet, but boron is an exception to the rule. It does not want an octet, so we are good to go. So around the central atom we have 3, which is trigonal planar. No lone pairs, so we'll keep it as 3 with no lone pairs. So let's draw it out here. I'll put the dots. I'm going to name it. It's a trigonal planar. And again, I'm going to have to check 2 different types of electronegativity. I'm going to have to check my BR and my BCl to see what's happening here. So boron is 2.0. Bromine is 2.8. Chlorine is 3.0. So for the first one, I've got a difference of 0.8. So this is a polar covalent bond. For the second one, I've got a difference of 0.5. I've got a difference of 1.0, also polar covalent. However, the ones that are 1.0 are much bigger than, not much bigger, but bigger than the one that is between B and Br. So if I were to add them together, they would not go back to the beginning. So this is going to be polar covalent overall. There's some practice questions. Hooray!